So, what are the functions used, the color functions used in a symmetric net with bag? Now you know the idea about symmetric net with bags, and we'll get into more details of how we manipulate colors. So first, there will be new functions basically. Here, let's have a small example. So this is a transition with some functions in output, and on the right part of the slide you see what it generates. So here I take a non-colored token and I generate a free variable into a place of the of course the type of this place is also the type of this variable, and it's exactly the same as for symmetric nets. You just have one token. This token has a value. C.all, you already know it. It's the function that will, the constant function that will generate one token per value in the color class. So here, A, B, C, you have A, B, C, 3 tokens. Here, it's a little bit different. The output place PS is not typed by C, but it types by bag of C. It means that, in fact, I will have a token that itself contains a list of elements, possibly nil. So this is noted here. So here I build by convention, but it's just a convention, we note with capital letters variables representing bag. It makes it easier to read, but it's just a convention. But the important information are the curly brackets you have that surround a variable x. And it makes that you are creating a token, and this token is itself a bag. And here I have the equivalent of the .all function, but applied to a bag that generates a token, but that embed a bag with one copy of every values you have in the color. So there is a difference. Here I have tokens, and here I have tokens that embed bags. This is the reason why we have a circle around. Okay, the first one, the one you have here, embeds a singleton, so the bag inside just has one element, and here the bag embedded in the token embeds all the values of the color type. And also you have functions to manipulate bags. So here let's imagine we have two places in input with color domain C, and here I have again output place with the same color domain C, but at one time I will use bags to manipulate tokens. So here I take a bag Y1 and another bag Y2. These two places are of the same type. So I can imagine that here I will do the union of these two sets. So I will create a bag that will have the set of the first bag and the set of the second bag. So this is what you have here. P1 and P3. Here I fire with Y1 taking two tokens from P1 and Y2 taking two tokens from P2. And the union of those is a bag with 4 tokens. But since the color domain is not a bag of C but C itself, it's split again into separated tokens. So I get the cardinality of the bag I built for transition T on this arc is 4 tokens, and then I get 4 tokens in PU. And you can also apply the set difference, okay, to place PG. Here, I will have remaining in P2, okay, it's the same marking. I leave 1 token in P2. But what's going on is that I will make a set difference from the tokens in the bag Y1. I will subtract all the tokens I found that are common in the bag Y2. And so I end with just 1 token, because it's once again, the bag is here not preserved, it's just used for the execution, the firing of the transition. And of course you have some other functions, some other useful functions. You have ORD that it was also available for symmetric nets. It allows you to get the position of the value in the color class. You have the unique that will ensure that within Y you will have only one value. In fact, the Y will be a set and not a multi-set. Okay, in fact, you will ensure that every value will be represented at most once, and you have the cardinality that allows you to get the number of elements that are in the token embedding a bag. So, as a conclusion of this sequence, you see that at this stage, symmetric bags are built on top, symmetric net with bags, sorry, are built on top of symmetric net by just adding specific functions allowing the manipulation of bags into tokens. So it's a higher level way to type tokens in such Petri net, and that you can also use such functions in guards, and everything together will preserve the symbolic reachability graph.